Now we're given a nice polynomial equation, a polynomial function that has all integer coefficients, no fractional coefficients, no decimals, all whole numbers on the coefficients. F of x equals 2x cubed minus 3x squared minus 11x plus 6. We're asked to find a list of all the possible rational zeros. And then part B, they ask us to look at the graph. We're not supposed to be noticing the graph for part A, but for part B, we're going to look at the graph and decide which of the zeros turned out to be the actual true zeros from the list in part A. Okay, so let's jump to part A, rational zero theorem. Okay, we've got integer coefficients in our f of x, so we can state that the form of any rational zero, p over q, I write it as p over q because it's a fraction. It's the factor of the constant coefficient on the top over a factor of the lead coefficient on the bottom. So what is the constant coefficient? It's a number at the end. It's 6. And what is the lead coefficient in that polynomial f of x? It's a number multiplying the highest power of x. It's a number 2. So let's list the factors of 6 on the top and then list the factors of 2 on the bottom. Okay, so we've got the number 6 from the end. That was the constant coefficient. And we write, well, factors would be plus or minus 1, plus or minus 2, plus or minus 3, or plus or minus 6. That's all of the factors of 6. What are all the factors of 2? That's easy. That's plus or minus 1, plus or minus 2. We're going to take this P over Q list and we're going to form it into a set of numbers. So first of all, the plus or minuses are annoying, so let's bring them out in the front and write a big plus or minus in the front. Now I'm circling this because if you forget this, you're losing half the points of the question, this first part of the question, because you have to consider both the positive and the negative roots, potential roots. Okay, so we're going to take all the numbers on the top and put them over the first denominator 1 and continue with the list with all the numbers on the top again over the second denominator 2. So we've got 1 over 1, comma, 2 over 1, comma, 3 over 1, comma, 6 over 1. Now we list the values over 2, 1 over 2, 2 over 2, 3 over 2, and 6 over 2. And now we simplify, and remember that you don't ever repeat yourself. So if we have any repeated numbers, we're going to throw them out. And we end up getting 1, 2, 3, 6, 1/2 and 3/2. That's getting rid of any repeated numbers. And don't forget that plus or minus in the front. Don't lose those points. So there's the list of all numbers that have factors of the constant coefficient on the top over factors of the lead coefficient on the bottom. Okay? So if there is a rational zero for this function, it is in that list somewhere. All of them might not be rational zeros, but if there is one, it's in that list. Okay, now let's answer the part B. From the graph, decide which of these zeros actually turn out to be genuine zeros, roots of the function. Well, look at the graph. We see a crossing at the x-intercept -2, that's a root. -2 is a root. We see 1/2 where it crosses, that's a root. And 3 is a root. So we have -2, 1/2, and 3. And those are all rational roots. In other words, they can be written as an integer over a non-zero integer. So our roots are zeros, in other words, just by observation of the graph, are the set of numbers -2, 1/2, and 3. And each of those 3 numbers appears somewhere in that list for part A, which makes me feel very satisfied that I had a substantial enough list that included all possible rational roots.